we will continue with the topic of membranes. Membranes are very important in removing solids for purification, on separating out proteins based on their molecular weight, and because they are operated at room temperature, it can be used for biomolecules and we can be very sure that they will not lose their activity. In the previous class I introduced the concept of membranes, so we shall continue with the same topic. So membranes are about 150 micron thick, and you also have thin membranes which are 1 micron thick. That means you can have really very thin polymeric material which can act as a barrier. If you look at the total worldwide consumption of membranes, this is a 2001 data based on the surface area, 85% is RO membranes, that means reverse osmosis composite membranes, and then you have the nanofiltration membranes coming in, you have again nanofiltration made up of composite material, you have polysulfone membranes and then microfiltration membranes. So a large number of membranes are used for reverse osmosis. As I had mentioned in the previous class, reverse osmosis is used for desalination of water, removing all the dissolved salts present in water, and the end product is something that is drinkable or potable. So different types of membranes, again this slide you might have seen in the previous class. You have the microfiltration, ultrafiltration, nanofiltration and so on. So it is good for concentration, it is good for recovery of the desired product, it is good for removing a lot of salts or solids present in aqueous streams. Then we have the reverse osmosis, it is used for desalination of water, so it can be used for demineralization and preparing potable water. Then we have the dialysis and electrodialysis. Dialysis is used in hospitals where patients have problems with their kidney, where they are not able to separate out urea. Then we have the electrodialysis, which works on the principle of using an electric field for separating cations and anions. Then we have the gas separation membranes for splitting gas streams based on the diffusion coefficient of the gas streams. Then we have the pervaporation membranes, where you are having a certain solute which will sort of evaporate and then it will permeate through the membrane material. So pervaporation membranes does not have any pores like a filtration, but here there is a diffusion of the solutes take place. So that is what is called a pervaporation membrane. Now there are certain broad categories under which each membrane could be grouped into, and that is what this slide and the next slide is going to tell you. If you look at microfiltration, generally the pressure is reasonably good, that means it is operating at either vacuum or at near atmospheric pressure, so it can remove large particles, 10 micron particles. So the principle is based on sieving, that means it has got lot of pores, and depending upon the pore size, if the particles are larger than the pore size, they get captured and smaller particles and salts travel through. That is what a microfiltration does. If you go to ultrafiltration, here the pore sizes are much smaller, that is why you are able to capture much smaller particles, hence the pressure drop is also very high. So the driving force is almost 10 bar here, you can see this 10 bar. Again the principle is the same, you have a sieving action, that means there are pores. Now when you come to reverse osmosis RO membrane, the pressures are extremely large, we can even have 100 bar pressure here, okay, and there are no pores here because there is an osmotic pressure and then you are applying pressure against the osmotic pressure. So there is a diffusion type of phenomena taking place, that is how reverse osmosis works actually. Now when you come to dialysis, dialysis is based on concentration. Like I said, dialysis is used for patients who have problem with the kidney, so the salts, the urea present in the blood will travel through the dialysis membrane and come to the other side, thereby the blood gets purified from salts. Okay. Again the principle here is diffusion and sieving. Electrodialysis, you are applying a large electric field, so the cations or anions get separated based on the direction in which you are applying the electric field. So we can separate out material or compounds molecular weight less than 200. So there is an ion migration taking place in an electrodialysis. So in electrodialysis we can have cation selective membranes, anion selective membranes and so on actually. That means the cation membranes will allow only cations to pass through, it will not allow any anions. Anion selective membranes will just pass anions, it will not allow any cations. So where do you use membranes? We can use it for separating out suspended solid, but generally for suspended large solids we use normal filtration. We can use it for divalent or multivalent salts, we can use it for monovalent salts, we can use it for bacteria, fungi, other proteins, biopolymers and so on. So we can use these separations. So if you have inorganic salts, molecular weight 10 to 100 and size 0.1 to 0.2 nanometer, RO membrane is good. If you have simple organic substances, again acids, sugars, molecular weight 100 to 500, size about 0.4 to 1 nanometer, that means they are slightly big, again RO is big, good. If you have antibiotics and I want to separate out antibiotics in the molecular weight range of 400 to 1000, size is also pretty large, 0.8 nanometers to 1.2 nanometers. Again we can use a RO type of membrane and it is really good. Then if you have biopolymers, what is a biopolymer? Biopolymers could be proteins, it could be enzymes, it could be polysaccharides, very large molecular weight biopolymers. We are talking in terms of 10 power 4 to 10 power 6 Dalton. So big size 2 to 10 nanometers. So here we can use ultrafiltration type of system because the sizes are much larger here unlike the other cases. If you want to separate virus, colloids, bacterial cells, yeast, fungi, the sizes are much larger, so we can use ultrafiltration, microfiltration, dialysis, so many different types of techniques are possible depending upon the nature of product and what is present in addition to the material you want to filter out. Now let us look at the material of construction of some of these membranes. If you look at RO and nanofiltration membranes, they are made up of cellulose acetate. Cellulose being hydrophilic, it will favor hydrophilic compounds. If you look at ultrafiltration membranes, they are made up of ceramic, polysulfone, polyvinylidene difluoride, that is PVDF, polyvinylidene difluoride, and cellulose acetate, that is Ca. If you look at microfiltration, it is made up of ceramic, polypropylene, that means we can go up to highly hydrophobic material, polysulfone, again polyvinylidene difluoride, so different types of material. Operating pressures varies quite a lot depending upon the type of process which we are undertaking. Reverse osmosis, as I said, very high pressure. If you go to nanofiltration, it may be 5 to 35 bar, that is step less. If you go to ultrafiltration, we are talking about 1 to 10 bars. If you are talking about microfiltration, it is almost atmospheric pressure system. So sometimes if you want to do a RO type of job, you may have an ultrafiltration before to capture as much as dissolved solids and suspended solids, then you may go to a RO type of membrane. If you look at the pore size of RO, it is very small, practically no pore size at all, and if you look at ultrafiltration, pore sizes are much larger, microfiltration is much larger pore sizes. Now you have to keep this in mind that you cannot have very high temperature of operation if you are using membrane. So cellulose acetate, we can go only up to 35 degrees, so if the solution is very hot you need to cool it down. If you look at PVDF, we can go quite high, almost 95 degrees, polysulfone composites about 80 degrees, and carrageenan is about 80 to 90 degrees. So biopolymer type of material, hydrophilic material, temperatures always have to be very less. Hydrophobic synthetic polymers, if you are using even polycarbonate or polyethylenes, we can go up in temperature of operation. Now the separation takes place because of equilibrium distribution or partition coefficient and so on, or it takes place because of the transport rates. Some material travels faster, some material travels slower. So materials that travels faster move from one side of the chamber to the other side, materials travelling slower will be left behind. So it is based on either equilibrium or it is based on differences in transport. These are the principles by which it works. Now last class I introduced that there are two models using which we can try to approximately model the membrane process. It is either a capillary flow model or it is a solution diffusion model. So in a capillary flow model, what happens, you have like particles, you have interstices and capillary like. So the liquid flows, particles which are very small, particles which are smaller than those holes will travel with the solution or solvent, larger particles will get entrapped. So that is the capillary flow model. In the solution diffusion model, there is just a diffusion taking place, a fixed law of diffusion like. So it is based on the concentration gradient. So many systems may have combination of both, if you take whereas some systems will just depend upon only one type of model. For example, if you are talking about sieving, then it will be a capillary flow model. If you are talking about a thing like pervaporation, it could be a diffusion model. Now as the membrane process takes place and if the vapor or liquid flows perpendicular to the membrane surface, okay, what happens, this is the membrane surface. I said there is going to be an accumulation of solute near the upstream surface of the membrane. This is called the concentration polarization. Okay. So normally the concentration near the upstream will be much larger than the bulk concentration. If Cb is your bulk concentration and Cs is the concentration near the surface, Cs will be much larger than Cb. This is called concentration polarization. It is not really good because as time flows, because Cs is larger than Cb, the diffusion of the solute from the bulk coming down to the surface on the upstream of the membrane is going to get slowed down because of this concentration polarization. Okay. And assume this is as your boundary layer, that is your boundary layer, there is always going to be a mass transfer boundary layer. Okay. This concentration polarization increases solute leakage through the membrane, particularly in RO, because the concentration on the upstream very near the surface of the membrane is large, so there is going to be a solution leakage. Whereas build-up of solute particles on the membrane surface will act as a barrier for microfiltration and ultrafiltration, because the diffusion of the solute from the bulk coming near the upstream of the surface of the membrane is going to get slowed down, because the Cs, that is the concentration near the surface, is much larger than Cb, which is the concentration near the bulk. Now let us look at some mathematical jugglery and calculate what will be the concentration polarization as we move from the bulk of the liquid right to the surface of the upstream of your membrane. Now you use a fixed law of diffusion for doing this, okay, because whatever solute that is getting carried towards the membrane surface will be equal to the material that is passing through the membrane. Okay. So the flux J is equal to minus d, that is the diffusion coefficient, dC by dx. C we can call it the concentration, x is here the distance, okay, that is the boundary layer distance, that is along the direction of the flow. So what will be the units of diffusion coefficient? It will be distance squared by time. Now the boundary conditions, what are the boundary conditions? That means add the wall on the upstream side you are going to have C is equal to Cs, and at x equal to D, that is the boundary layer, C is going to be Cb. So we can just solve this differential equation and we can apply these boundary conditions. If we do that, what will happen? We get a nice equation. Okay, this is a first order differential equation, so it is very simple to solve. So we will get J equal to D divided by D logarithm of Cs by Cb. Cs is the concentration of the solute on the upstream because of the concentration polarization near the surface of the membrane upstream, and Cb is the concentration in the bulk, right. Cs will be larger than Cb. Now d by d, that is d is the diffusion coefficient, and this d is the thickness of your boundary layer. Okay. Now this is called the mass transfer coefficient, d by d, and it will have units of distance by time. Okay. Units of distance by time. So we have a equation which tells you the flux of the solute will be a function of the mass transfer coefficient and the logarithm of the concentration and the upstream near the surface of the membrane divided by the concentration of the solute in the bulk region. Now what are the factors that affect your separation processes in membrane? Two factors you need to keep in mind. One is the concentration polarization, like we talked about. In ultrafiltration it will slow down the process, in RO it will allow, there will be a leakage of the solute on the other side because Cs is very large. So one factor which affects is the concentration polarization. The other factor is the fouling of the membrane. Now this is a long term process, this is an irreversible. Concentration polarization I see at least is reversible, I can stop the process and I can do some cleaning and then again I start my membrane process, Cs will be equal to Cb. So it is a reversible process, it is a very short term effect, whereas the fouling is a long term effect and it is irreversible. Fouling happens because of so many factors. Fouling happens because of bacterial material present, fouling happens because of the dissolved salts that are present, fouling happens because changes in pH which will allow your salt to precipitate out, fouling happens because of colloidal suspension which gets agglomerated and so on. So all these factors lead to fouling, and there is going to be a deposit of material on the upstream surface of your membrane. So the entire membrane filtration gets slowed down as time goes on. So the flux gets affected over a period of time because of slime formation, because of microbial growth, that means you can have bacteria, algae, fungal, all those things, deposition of macromolecules especially in ultrafiltration membranes, because ultrafiltration may be having a lot of proteins and other material, colloidal deposition, lot of colloids, salts, physical compaction of membrane, because you are applying such high pressure especially in RO that the whole membrane gets collapsed and get compressed, that is called the physical compaction. So all these factors affect your filtration process, it gets slowed down and slowed down, and after some time it is not very efficient to run your membrane, so you need to stop and you need to remove all the fouling, or if it is irreversible you need to completely change your membrane. So that becomes very expensive, changing a membrane is very expensive because most of the cost is the cost of the membrane. So you can inhibit fouling, you can slow down fouling by doing many things. We can make the surface very hydrophilic, so bacterial proteins and other things do not deposit. We can do some pre-treatment of the feed, the feed can be pre-treated so that there are no salt precipitating out. We can do pH adjustment, or we can even precipitate all the salts before they come to the membrane. So you can have a precipitation chamber and then you can move it to the membrane chamber. Then you can do lot of frequent cleaning of the membrane with chemicals, okay, that also possible. So we can clean the membrane surface from time to time. Then we can do a back flushing, that means we can send the feed from opposite direction so that whatever fouling that has taken place will get dislodged and removed from the surface of the membrane. So there are many ways by which we can do a flushing. We can do a forward flushing, we can do a backward flushing, we can use air flushing, that means we can just pass air so that the foulants that has been settled gets dislodged. We can use a chemical cleaning, so all these can be done. Okay, how do we prevent or decrease fouling? You cannot completely prevent fouling, we can decrease it or we can slow it down. So we can add biocides so that there is no biofouling, we can add insecticides, another chemicals which will prevent the attachment of microorganism on the surface. When microorganisms settle down, they form exopolysaccharides, they form dead biocells, live cells, proteins, carbohydrates. So they form something called a biofilm on top of the membrane, and that completely blocks the flow of your solution. Changes in pH, we can change the pH so that salts do not precipitate out. So if the salts start precipitating out, you are going to have a lot of fouling. Another approach, we can add a pre-filter, that means we can have another filtration setup which can remove most of the dissolved solids, or if there are suspended solids we can have a simple sieving filter which will remove all the suspended solids. So we can remove most of this type of solids by incorporating a pre-filter in the process. So membranes reject dissolved solids, but then they are very inefficient if feed contains suspended solids. So it is not very good to have suspended solids if you want to resort to membrane, or if the solids start precipitating out during the membrane process. When does solids precipitate out? It can precipitate out if there is going to be change in pH, or if there is going to be a colloid and agglomeration formation. So prior to the membrane filtration we need to have a lot of pre-processing. So we need to remove all the suspended solids, we need to remove oxidizers because some oxidation material may spoil the membrane surface. If there are anything that is going to precipitate out, we need to precipitate out. Then if there are any dissolved solids, we can alter the pH so that the dissolved solids precipitated out. We can also have a pre-filter so that if there are any hard sharp particles, it may come and hit the membrane surface and break it, mechanically physically break it. So we can have a pre-filter. Then we can add a biocide or a fungicide so that you prevent bacterial growth. So all these various operations you can perform before you take your solution for membrane operation. So you see that doing a membrane operation is not straightforward, you may have to resort to quite a lot of pre-processing. Conventional membrane filtration, you may have a chamber, you have the membrane, okay. So this is an upstream and a downstream. So the liquid is pumped in, the pressure depends upon the type of membrane process you are resorting it to. So the concentrated solution is on the upstream side of it, and this is going to be forming concentration polarization, and here the filtrate moves on the right hand side. So if we increase the velocity of the liquid flow, then it may create turbulence, so it may decrease the boundary layer. So when you decrease the boundary layer, obviously mass transfer coefficient is be better, because mass transfer coefficient is given by diffusion coefficient divided by the boundary layer. So if I make the denominator smaller, you are going to have higher mass transfer. Another way by which you can reduce the concentration polarization is using a cross flow filtration. So far what we saw is a perpendicular flow, that means the flow is perpendicular to the membrane surface, or the membrane surface is perpendicular to the flow direction, okay, or that it is also called dead end filtration. So normal filtration is also called dead end or perpendicular filtration. In a cross flow filtration, the feed is also pumped tangentially across the membrane surface, that means instead of perpendicular it is almost flowing parallel. That way you are preventing the formation of the boundary layer, you are also preventing the formation of the concentration polarization. So the advantage will be flux will not get reduced with filtration. So that is the main advantage when you do a cross flow filtration. This is a typical picture of a cross flow filtration. If you remember how we had the normal dead end filtration where the flow direction is perpendicular to the membrane surface, here you can see the flow direction is parallel to the membrane surface. So that is why it is called a cross flow filtration. So here you are not going to have any concentration polarization and boundary layer formed. So we can have much longer filtration process when compared to the dead end filtration process. So fouling also gets reduced because your liquid is flowing parallel to the surface, so the boundary layer is not getting formed, okay, and even if there is a biofilm formed it gets dislodged or washed out or removed, okay. There are many operational requirements in a membrane process, so you need to keep all those points in mind. We want to have very good selectivity, we want to have high separation efficiency, so this is the fundamental point. We want to have high permeate flux rate, that means the rate of filtration has to be very good. The membrane should have good mechanical and physical strength to withstand the high pressure. Continuously you are operating at such high pressure, so your mechanical strength should be quite high. The pores should not get elongated because you are continuously applying a mechanical force. Durable, it should be durable and the performance should be constant over a prolonged period of time. So that means the performance should not vary with time. It should be resistant to corrosion, that means it should not corrode, that means whatever material you are filtering and the membrane material have to be compatible with each other. It is easy to fabricate, I mean you should not have very complicated process and it should be of appropriate shape. I may be using a flat plate membrane, I may be using tubular membrane and so on, so it should be easy to fabricate of the shape we want to have. It should be of low cost. Cost is the most important thing, and although we say it should be of low cost, the cost of replacing the membrane is the most difficult and the cost of replacing the membrane is very high, and so the operating cost involves this cost, and if we can reduce the membrane replacement cost or if you can prolong the membrane life, your operating cost will definitely come down, and it should be readily available, of course, that is obvious. If we take a reverse osmosis membrane where we are removing dissolved monovalent salts, where we are applying very high pressure, it should be able to discriminate the low molecular weight solutes and ions and solvent. So the solvent should be passing through the membrane, whereas these very small ions or low molecular weight solutes should be retained by the membrane. So it should have that differentiating capacity because we are working at molecular sizes of solvent as well as smaller ionic sizes. So if you take aqueous solution of simple electrolytes and low molecular weight material like less than 500 Dalton, the molecular dimensions of the solute and the solvent will be comparable, okay. So you need to keep that point in mind. Now reverse osmosis will be very large, so our reverse osmosis membrane should be operating at almost 50 to 60 atmosphere pressure. Now as you keep filtering or as the membrane process keeps taking place, there is always a decrease in flux over a period of time at constant pressure. That means we are applying the same pressure but still the flux will keep decreasing, and Hermans and Brady have developed a model which is given by this particular equation, d square T by dV square, that is second derivative of the inverse of dV V and T is equal to K into dt by dV raised to the power n. T is your filtration time, V is your cumulative filtrate volume, and K is any constant. Now n can take different numbers depending upon the type of assumption or the type of model which we have in mind. So if it is a cake filtration model, that means fouling occurs due to the formation of a bed of particles on the surface of the membrane, then n is considered as 0. If n is 0, then what do we say? d square T by dV square is equal to constant is equal to K. Okay. There is something called intermediate blocking model where particles settle on existing foulant deposit. That means there is a foulant deposit, that particles start settling. In that case n is equal to 1. Then we have something called pore constriction model. Foulants are deposited on the inner surface of the pore. So as the foulants start depositing on the inner surface of the pore, the diameter of those pores becomes smaller and smaller. That means it decreases with time as the foulants start settling down. There we take n is equal to 1.5. Now fouling occurs by complete blocking of the pore, then n becomes 2. So you see, we can put different n values depending upon the type of model or type of assumptions one takes into notice or one considers. Okay. Now dt by dV, that is on the right hand side, which we have is the inverse of the instantaneous filtrate flow rate, because V is the volume, okay, dV by dt is the filtrate flow rate, dt by dV will be the inverse of that. Now dt square by dV square is proportional to the rate of increase in the total resistance to filtration, that is what is on the left hand side, that is rate of increase in the total resistance to filtration. So if you assume a uniform cake resistance, then we can integrate that equation and we end up with a equation like this with the exponential term. That means the flow rate will keep uniformly decreasing. Let us look at what each term is in the next slide. So here you have Q equal to, that is volumetric flow rate, Q naught is the initial volumetric flow rate to the unfouled membrane. There are exponential terms coming here, okay. Alpha is the area blocked per mass of deposit, delta P is the transmembrane pressure drop, mu is your fluid viscosity, Cb is the bulk mass concentration of foulant, Rm is your clean membrane hydraulic resistance, Rp naught resistance of the initial foulant deposit, F is your fraction of the bulk concentration that contributes to deposit growth, Rp is the time dependent resistance of the growing cake, and alpha S is the specific resistance of the foulant cake. So you have a large number of parameters coming into picture, resistance offered by the deposit, resistance offered by your membrane material, cake resistance, area blocked because of the deposit and so on. So this is how this flow happens as a function of time when there is going to be some sort of a deposit. The deposit could be various type, so the n could be ranging from 0 to 2. Now if you take a cross flow membrane, the pressure drop in the cross flow membrane will be made up of 3 terms: pressure drop across the membrane material, across the polarization layer, and across the cake layer. So you are having 3 pressure drops which will add up to overall pressure drop. So you need to keep that in mind: pressure drop because of the membrane material, pressure drop because of the polarization, pressure drop because of across the cake. Now the permeate flux, that means rate at which the liquid flows from the upstream to the downstream, will contain 2 very important terms: the permeability L, or 1 by L is called the Rm, membrane resistance, and the delta P. delta P is the driving force, the pressure. So, the permeate flux will depend upon the permeability of the membrane material and the driving force. Now, of course, osmotic pressure is also going to play a role. Osmotic pressure will reduce the flux, that is, it will decrease the driving force. Do you understand? So, you are filtering and there is an osmotic pressure because the permeate has very low concentration of your solute. So, it is going to reduce the driving force. So, in that situation the driving force will get changed here. So, the flux will be equal to the permeability multiplied by delta P minus S POS. POS is the osmotic pressure and S can take a 0 or 1 value. If the solute is completely rejected by the membrane, then S will be 1. If the solids or solute is completely passed, then S is equal to 0. That means if solids completely move the other side, then the osmotic pressure has no effect on the driving force, whereas if the solute is completely captured, that means on the downstream you have pure solvent without the solute, then osmotic pressure will have a maximum effect because S will take the value of 1. So, S takes value of 0 or 1 and it is 0 if the solute or solids get completely passed. So, the effect of osmotic pressure is completely felt on the membrane process. So, the delta P gets decreased because of the osmotic pressure. Okay. So, if S is equal to 1, that means completely rejected. If S is equal to 2, that means the solid is completely passed. So, if S is equal to 0, what happens? You have only L into delta P. So, the osmotic pressure is not felt, whereas if S is equal to 1, you have delta P minus POS, which is osmotic pressure. So, maximum osmotic pressure is felt in and the rate of filtration goes down. So, we will look at some problems later on this. So, the permeability varies depending upon the type of membrane material we use. So, different membrane materials may have different L values. Generally, the manufacturer provides us with the value for L. Now, let us look at the flux of the solvent. The flux of the solvent will be dV by dt, that is the volume of the solvent retained, that is equal to minus Aj. J is your flux, A is the area. So, this is given by J is given by L delta P 1 minus the osmotic pressure value here, assuming S is equal to 1 here. Okay. We will look at this osmotic pressure later, how to define osmotic pressure in terms of concentration based on Van 't Hoff's relation. So, we will talk about that later, but for the time being we will assume this. This equation can be integrated assuming at t equal to 0, V is equal to V0, correct. So, if you do that, we will end up with a relation like this, T is equal to 1 by AL delta P and so on actually. Okay. We will talk about the relationship between concentration of the solute dissolved and the osmotic pressure later. Now, the average permeability, that is, look at the units, liter per meter square per hour per bar. Bar is the pressure, hour is the time, meter square comes out in because of the area. Okay. For polyamide urea membrane is 3.8, and if you look at polyamide on polysulfone support, it is around 11 to 15. Water permeability for gamma alumina, cobalt alumina and zinc alumina are 1.2, 5.7, 3.5. So, these numbers vary depending upon the type of inorganic materials you use. So, you can also make membranes with alumina. We talked about so many polymeric materials, PVDF and polyethylene, polycarbonate, polyacrylamide, cellulose acetate and so on. So we can make with inorganic materials, so like alumina, titania and zirconia. So there are companies which manufacture this type of membranes, TAMI Industries. The permeability of such membranes in terms of ml per centimeter square minute psi is 0.0129 or 0.0131 or 0.0055 for a molecular cutoff of 50, 15 and 1 kilodalton. The advantage of inorganic membranes are they can withstand temperatures, that is the main advantage. Structure of membranes. So the membrane will have two phases. You will have a thin dense layer of material with microporous structures. So this could be about 0.5 to 10 microns. Structure covers the top of the membrane and it is supported by a thick layer 50 to 125 microns of macroporous material. Okay. So the bottom layer gives the strength to the membrane, the top layer is responsible for the basic separation. So the top layer may be 0.5 to 10 microns, so the bottom layer could be thick 50 to 125 microns. So you generally make it into a single casting process, top and the porous support to give a membrane thickness of 0.1 to 0.2 mm depending upon the type of membrane. So later then you support the membrane on a rigid porous backing surface. Okay. Typical equipment, if I want to have a membrane, I may have a feed tank, I may have a pump, I may have the membrane module. So the solution flows, this is like a cross flow and then it comes back, so there is a permeation taking place. So if it is a concentration, the aqueous liquid flows, so this liquid that is going back is getting concentrated more and more. Okay. Whereas if it is separating out certain particles, again the same thing happens in this process. Okay. So this is a typical equipment for performing a membrane operation. So you will have a feed tank, and we will have, as I explained before, we may have a pre-filter to filter out suspended solids, we may have a precipitator where we may be adjusting pH to precipitate your dissolved solids, we may have a tank where we may be adding a biocide or a fungicide so that the liquid does not form a biofilm or bacterial layer on top of the membrane surface. So all these are done, so those such smaller vessels are also incorporated in your flow diagram. Okay. So different membrane modules have been designed based on the criteria of your selection. So generally our goal is to have a very high surface area to volume. Why are we doing that? We want to minimize the space requirement. If you are minimizing the space requirement, we are minimizing the capital cost. We will have to have good structural support, because if the membranes are very thin, we need a good backing structural support if we are operating at very high pressure, otherwise the thin membranes will just break. We want to maintain a very low pressure drop on the downstream, that is on the concentrate side of the membrane, so that to maintain the driving force for the permeation. We want to have a good turbulence, so that we want to minimize fouling, we want to have minimize concentration polarization. We should have provision for back flushing and replacement of membrane. That means I should be able to, after 1000 hours or so many 100 hours, I should be able to back flush and remove the foulant. I should also have the provision for replacement of the membrane, because you may be doing back flushing many times, but after some time the membranes has been fouled so much, there is no hope of recovering its performance, so we may have to replace the membrane. So there has to be facilities for performing this type of job as well actually. So different types of membrane modules are there. the flat sheet membrane, that is like a plate and frame. You have a plate, so the membrane material is in the form of a plate, and then you have a frame, so the frame holds the flat plates. You can have a spiral wound membrane, that means the membrane is wound like a spiral. You can have a tubular membrane, that means a long tube and the surface is made up of membrane and the liquid flows inside. You can have hollow fiber modules, that means it is like a shell and tube heat exchanger. You can have a lot of hollow fibers, and membrane process takes place because of the flow in the inside. So these are just some pictorial representation of different designs of membranes. Okay. So this is a tubular membrane. So it is a tube and the walls are made up of the membrane material. Okay. So the slurry flows and the liquid or the solvent may permeate out through the surface of these tubes. So in this side you may end up having concentrated liquid. This is a plate and frame type of design. You have the membrane, you have the frame which holds the membrane. So the flow is happening here, liquid is flowing here. So if I want to increase the surface area, I may have many plates and many frames stuck together. It is very simple here. If I want to replace the frame, what do? I mean, if I want to replace the membrane, I will just remove these frames, I will remove this sheet of membrane, I will put another sheet of membrane. So job is quite simple. So increasing the surface area, I will put many plates and frames, that is how I increase the surface area of the membrane process. The third design is like a shell and tube. So you have many tubes of membranes, so your liquid may be flowing here and they get distributed along the tubes, and on the other side you may have a concentrated liquid flow here, and your solvent or water may be flowing out of the solution. So this is another design. So if you want to replace a tube, you need to open up this heat exchanger pipe, take one of these tubes which might have been fouled beyond use or might have been physically mechanically damaged, then you can put another tube here and carry out your job. So that is another way of looking at this type of shell and plate type of design actually. So you have large designs possible, and especially if you are working with the polymeric material, you will be able to cast different types of membrane designs. That is the main advantage of working with the polymeric material, whereas if you are working with the inorganic material like ceramic and so on, it may be quite difficult to cast or prepare those type of material of required shape or size or form in which you would like to have it. Okay. Flat sheet membrane, let us look at this flat sheet membrane. They are used in plate and frame type of design. So we can have multiple layer of sandwich of different types of membranes stuck together. It is like a filter press, so it is easy to fabricate. So we can compactly design it and structure it. It can even work under quite a good pressure drop. Here we are talking in terms of 30 to 4 kg per centimeter square. Main disadvantage, surface area is small, that means I need to have several plate and frame designs to achieve the required surface area. So that is the main disadvantage with the flat sheet membrane. Although I can just make the membrane in one design, large sheets, I can cut the sheets to the desired size of my frame and bolt it to the frame. So the fabrication and setting up of my membrane unit is easy, but the major drawback is my surface area per separator volume will be very less. So it is not good enough. I may have to put several stacks of plate and frame design. that is the main disadvantage of flat sheet membrane. And another design is your spiral wound membrane. So how do you do it? You have a fabricated wound of a membrane sheet in double layer into a spiral. So you get it like a spiral. The feed is passed axially or spirally over the outer side of the double layer, okay. So the permeate also moves spirally to a pipe located at the center of the spiral. So it liquid flows in a spiral manner, so we get a very large surface to volume ratio. But one thing you have to be careful about is your feed has to be quite clean. It should not have any particulate matter, because as the liquid flows in a spiral manner, if there are any particulate matter, it may damage the membrane surface. So the spiral wound membrane advantage is it will have very large surface area to volume when compared to your flat sheet, but be careful that particulate matter does not spoil or damage the entire spiral. Whereas if there is a particulate matter in a flat plate membrane, it may be damaging only one small area of your surface. So this is what spiral wound membrane is all about actually, okay.